to tell you, this is a longer process, and it's one of those things, there's not a shortcut to it. It's not something you're just going to look at and give an answer. It is more of a proof-based answer when we do it, so your answer is your explanation. So there's really no shortcutting it. You are explaining something to me. We've talked a little bit about limits. We've been calculating limits. We've done them from tables. We've done them from graphs. We were working on equations or expressions and talking about reducing and those kinds of things when we could plug in. But we really haven't got into the nitty-gritty, what is a limit actually. So that's what we're talking about now. So let's take a look at this function. Okay, this is a piecewise function. I have one piece when x is not equal to 3 and one piece when x is equal to 3. Now in terms of a limit, do we care what happens at 3? No. So in terms of the limit, would I ever really even use this second piece? No, it's really just a line. So if I asked you what the limit was as x approached 3, you would be able to just plug in a 3 and you would tell me 5, right? Okay, but why? So if I want to prove that it's 5, if I wanted to really justify that to someone, we have to be able to get our x close enough to 3 so that our y is close enough to 5 to prove it, okay? And you should be able to get as close as I ask. If it's really approaching 5, if I say I want to be within a tenth of 5, you should be able to give me an x to get there. Or if I want to be within 100th of 5, you should be able to provide me with an x to get there. So that's what the formal definition does. It kind of gives a standard for how to make it get as close as possible. We know distance is absolute value, gives you distance because distance is always positive. So we start getting into some weird looking symbols here. Okay, getting used to this notation. So we are trying to find a number. This symbol is called delta. It's a Greek letter. We use epsilons and deltas today. So those are just some Greek letters. Okay, so if it's saying the difference, the distance between f of x and 5, so your y value and 5, is less than 0.1 if the distance between x and 3 is less than delta. Okay. We know x isn't going to equal 3 exactly, so you could also see it as x minus, the absolute value of x minus 3 falls between 0 and delta. It's a little redundant because we know absolute value is already positive anyway, so you really don't have to include that. So I'm trying to justify how I might get there here. Let's say I took my 0.1, which is just a number I made up. I said I wanted to be within a tenth. Okay. If I divide that by 2, I get 0.05. Okay, look what happens. So right now I'm just giving you a lot of stuff. I'm kind of walking you through an example. You really don't know where I got any of these numbers. We're going to get there later. Right now I'm just kind of trying to get you used to some of the notation that we're going to see along the way. So the absolute value of f of x minus 5 equals, where did I get this 2x minus 1 from? Yeah, the original f of x. Wasn't f of x equal to 2x minus 1 right there? So I just plugged that in. Okay, then if you work through this, negative 1 minus 5 gives me negative 6. What could you pull out of that? A 2. It's positive, so it could come outside the absolute value, right? Okay, then right here I had 2 times the absolute value of x minus 3. At the very beginning I kind of made an assumption that the distance between x and 3 was going to be less than 0.05. So I was able to say this is less than 2 times 0.05, which is 0.1. In other words, if I wanted my y value to fall within 1/10 of 5, so I wanted my y to be between 4.9 and 5.1, I just found that my x has to be within 1/10, sorry, not 1. My x had to be within 0.05 of 3. So my x had to be a value between 2.95 and 3.05. Okay. You should be able to come up with that for any bound that I give you. So if I said, okay, you know what, 0.1 isn't close enough, I need to be within 0.01. Then you should be able to alter your x to make that happen. If you think about manufacturing, you know, when they make parts, is every part that's made identical? No, there are variations. So they have to have a range of acceptable values, right? And every piece, every step along the way in that process has to fall within a correct range so that the final product will work. So that's kind of like a limit here. How close do we have to be to make this work out at the end? All right. So this is the formal definition of a limit. It tells us let f be a function defined on some open interval that contains the number a, except possibly at a itself, because a limit doesn't care what happens at the point, just as you get close to it. Okay, we know this says the limit as x approaches a of f of x equals L. We've been evaluating those limits. What that means is if that limit is in fact true, this down here is what we are going to be using today. It means for every number, this curve E is what's called an epsilon. For every number epsilon greater than 0, there is a number, what did I tell you the symbol was? Delta. There's a delta greater than 0, such that this line is true. You can write it like this, you could drop that 0, so the distance between x minus a is less than delta. If that's true, then the distance between f of x and L is less than epsilon. Okay, this is one of the ugly pieces of calculus. Okay, this is something we're just trying to get our feet wet with this semester. We're not going to do a ton with it. We're going to spend a couple days, try to get used to not being scared when we see some weird looking symbols. We're really just going to be proving a lot of limits using this process. So that definition is something you will ultimately have to know. It'll probably be a question on your test. What's the formal definition of a limit? And we are going to write this on essentially every single problem that we do in this section. So I'm just going to, before we get into an actual example, the next 2 slides I just have kind of some more explanation about what this is saying, and then we'll start looking at how to do it. So the definition of a limit tells us that if we have any interval, epsilon is how far you are from the actual limit. So you would have your limit minus and your limit plus epsilon if you're trying to get a window of values. So if you pick this window around your limit, then you should be able to get a corresponding window around your x values. Your x minus a delta and your x plus a delta. So that if you pick any x value in this window, it will give you a corresponding y value in the window over there. Does that make sense? So we're trying to figure out how we can choose delta, that window for our x, to get something that will give us a window, a value in our y window. Okay, I know it's hard, bear with me. Okay, we're gonna get there. Doesn't make a lot of sense yet, but it will. This is just another picture of it. You know, this is your limit. Okay, we have epsilon, that's basically above and below. So you have to get a y value in this range. Okay, if my y value has to be in that range, then I have to look at where can my x's fall. And I have to pick an x down in this window so that my y falls up here. Okay, we're going to walk through some. This first one, we're just going to try to look at a graph a little bit to see if we can kind of get an understanding. And then we will talk about how to actually do one. So, use a graph. So you need a calculator. Get your Chromebook or your calculator out, please. So, what I'm asking you to do is to find a delta to make this true. That the distance between x cubed minus 5x plus 6 and 2 is less than 0.02. Sorry, 0.2. Okay. So let's just start here. This is representing my f of x. Okay. If my absolute value had to fall in that window, let's think about absolute value inequalities for a second. So thinking back to college algebra 2 days. A less than, is that an and or an or? And. So you could make one big inequality and put it between -2 and +2? Or -0.2 and +0.2? Okay. So I'm trying to get this function by itself. So what would I do with my -2 here? Okay, so if I add my 2 to everything, I get 1.8 less than x cubed minus 5x plus 6 is less than 2.2. Okay, I want you to go to your graphing calculator. I'm going to pull mine up on my computer so I can show you guys. Okay, I want you to go to your y equals. Clear out anything that you have in there. Okay, and I'm going to graph a couple different things here. I'm going to graph my function, my x cubed minus 5x plus 6. I'm also going to make my y2 my 1.8 I'm going to make my y3 2.2. I'm going to hit zoom number 6 for a second so we're all looking at the same thing. So there is my cubic function. I have my 1.8 and my 2.2. Probably going to have to zoom in a little bit before we can really see this, aren't we? So I'm going to zoom in and see if this helps. Okay, so we could talk about a couple different places. What I really want to look at is this piece right here. So my y value, I'm looking at the section of that little curve that falls between those two horizontal lines. Okay. Again, it happens a couple different times. It happens over here, it happens right here, and here, because your curve bounces back and forth. But let's just do one of them. So if I'm looking at this one right here, we need to find the x values that make it fall in that window, because I'm looking at the distance between x and 1. The absolute value of x minus 1. So that's why I'm choosing that section that's centered around 1. If I was doing as x approaches 1.5, you would be looking at this section over here. Does that make sense? So I need to find those points where my graph, my horizontal line meets my curve. Okay, our calculator can do that for us. Do you guys remember how? We're going to go to second, trace, intersect. So second, trace, intersect. It's going to ask us some questions. First curve, it tells you up at the top which curve it's on. It's on that blue one, the cubic, which is what I need. Just hit enter. Second curve, I want to find where it meets my black line first. So you just have to use your up and down arrows until you get it on the black line, the y equals 2.2. Hit enter. Guess, you need to get close to that intersection point and hit enter. And it tells me 0.9114. Okay. Now we need the second one, so you repeat. Second, trace, intersect. First curve, again, we just want that cubic. Second curve, I want the red line. Move over close to it, and I get 1.1240. Okay. So essentially, what that's telling me is if I pick an x value between 0.9114 and 1.124, then my y will be less than 2/10 from 2. Okay, we kind of found that window for our x's to match the window for the y's. Now, I know this probably still makes no sense, okay? This is one of those topics in calculus you have to be patient with me for a while. So it's not going to make sense right away, but we're going to get there, okay? Do you guys kind of understand how if you pick an x value between these two numbers, then your y falls in that the correct window that we were looking for. Kind of get what we were looking at on the graph there. Okay. Really what we are going to be doing is using this epsilon delta definition to prove that a limit is equal to a certain value. And it is not something that you necessarily need for Calc 1, but I can't just skip over it because if you go to college and you take higher level classes, it does come up. So I need you to have seen it before. Okay, so it's kind of one of those topics we're going to talk about now. We're not going to use ever again, really, outside of this lesson. I might put one on a quiz. I might put a bonus question on a test. Hint, hint. Do I have one on a quiz? When we get to the test, it might be a bonus question. But other than that, we're really not ever going to use it again. But I need you to have seen it in case you have to take those classes later on. All right. So we are going to spend the rest of the day just proving, using this definition to prove things. Why don't we, do you guys want to do another graph one? Do we need to show another one on the graph? No? Okay, then I'll skip this and we'll talk about the definition. So, the definition, you have to follow my process. I'm going to give you steps. You have to do it every single time. So you are going to start out with given epsilon greater than 0, and we're going to look at this. The f of x, the L, those are going to be given in the problem. It'll give us a function, it'll give us the limit. So we're going to start there to find a value for delta. So really we're going to start with some scratch work. And then we are going to prove the definition of the limit. So we're going to start with one. I want to prove that this is true. We all believe that this is true. I believe that if I plug my 3 in, I get 12 minus 5, which is 7. So we think that's true. We can make a table and show that we think it's true. We could look at a graph. But if I actually want to prove it to someone in the math world, you have to write a math proof. Okay, if you take any class beyond Calc 1, you have to write math proofs. So we're kind of getting our first taste of them here. So we're going to start out with really our work. Okay, our goal here, what I'm trying to do is show that if the absolute value of, we're using the definitions here, the absolute value between x and 3 is less than some number delta, then the absolute value of f of x, what's my f of x? Minus my L, what's my limit? 7 is less than epsilon. This is the definition. Actual definition, we said absolute value of, what letters did it use? X and A, x minus A is less than delta. Then the absolute value of f of x minus L is less than epsilon. That was the formal definition that I highlighted in that box. So that's our goal. We have to show that that's true. Once we've proven that that is true, then we have calculated, or we are done with our problem. So, step 1. We have to find the delta value. And so it kind of seems like cheating. We're really just going to work backwards. I have to figure out what delta would work. So I'm going to start with this. So my f of x minus my L. Okay, if you start simplifying in there, what can you do? Negative 5 minus 7 is negative 12. Then what could you do? It's positive, so it just comes out. Okay, haven't we seen this absolute value of x minus 3 before? That's right there. I need that to be less than delta, right? So we're working backwards from this, which is our end goal. I know that is less than epsilon, because we already said at the very beginning this will be less than epsilon. If I want to get my absolute value of x minus 3 by itself, what do we have to do? Divide by 4. Okay, if I do that, what that tells me is I need my delta to equal epsilon over 4. Right, that was just kind of my scratch work. So basically what that's telling me is if I said I want my y value to be within 0.5 of 7. That's like saying your epsilon is 0.5. Then you could turn around and tell me, okay, then your delta has to be 0.5 over 4, or 1/8. So you need to be within 1/8 of 3. So you would have to pick something between 2 and 7/8 and 3 and 1/8 to make that happen. So we basically found a formula to make it work. Now we're going to prove it, because these problems are all about the proof. So this was our work. Step 2 is the proof. And when we do that proof, we are using this definition. So we are going to start out by writing some things, and you have to write them on every step to have a complete proof, so on every problem. First thing I need to say is let my delta equal epsilon over 4. Then I'm going to write down the first half of the definition of a limit. So if the absolute value of x minus a, which my a value here was 3, is less than delta, then the absolute value of my f of x, which was my 4x minus 5, minus L. So kind of this goal statement, I'm having you write the same things over and over again so you get used to them. I'm using my goal statement, and I'm going to work now until I get a less than and an epsilon. Once I have my less than and my epsilon, I'm done. So let's start here. Oh, I shouldn't write L though. What was my L on this one? 7. Thank you. Now we're just going to redo exactly what we've already done once. We did it the first time just as work. Now we're doing it as a proof. So that is the absolute value of 4x minus 12. We'll pull out your 4 again. But what did we already assume about the absolute value of x minus 3? We said it was less than delta. So this would have to be less than a 4 delta. So you notice I just got my less than in the problem. I told you you were done once you got a less than and an epsilon. Okay, but what have we already said delta is equal to?
Epsilon over 4.
And 4 times epsilon over 4 is epsilon. So I got my less than, I got my epsilon. We are done. If you want, you can write a conclusion sentence at the end. So what we just proved is that the limit as x approaches 3 of 4x minus 5 does in fact equal 7. Very confusing right now. Just stay with me, okay? We're just going to practice. So just be patient. It gets easier, but it's one of those things we just have to keep going through them. They're all going to kind of start looking the same. We're going to have, it's very repetitive once we get into them.
Okay, so does the work like in the sentence? I'm confused about like the if, then the absolute value.
Yeah, this is,
Okay.
so kind of all one sentence. And
Okay.
this ends it right there. Other questions? I'm gonna, I don't know, can I get through one more? Let's try to do one more. I'm not giving you homework yet. We're not ready for homework yet. So we're just practicing. I want to do one more today, and then tomorrow we're just going to practice more of these. So our goal, the definition of a limit is if the absolute value between x and a, what's my a value here? 3, is less than delta, then the absolute value of my f of x, what's my f of x? 13x minus 29, minus my limit, which is 10, is less than epsilon. So I will be done when I've proven this. That's the definition, that's what we have to show. So to do it, we have to start with our work. We have to find delta. We find our delta working backwards from the end. So I'm going to start with this absolute value of 13x minus 29 minus 10. What can I do there? Combine like terms. Then what could you do? Lo and behold, I have that x minus 3 again, which we've already seen in our definition. We know we're kind of working from this statement where it's less than epsilon, so if this is less than epsilon, what should I do now? Divide by 13. So that tells me that delta needs to equal epsilon over 13. So that was our work. Find out what delta has to be. So it's epsilon over 13. Step 2 is the proof. First thing you have to do in your proof is tell me what delta is. So I'm going to say let delta equal epsilon over 13. Then we are going to basically recite our goal up until that less than epsilon part. And our work will have to get the less than and the epsilon. So if the absolute value of x minus 3 is less than delta, then the absolute value of 13x minus 29 minus 10, and we have to work this until we get the less than and the epsilon. Now from here, we've really already done this once, so it's really kind of regurgitating what we did earlier in our scratch work. So combining like terms. What can you pull out of that? 13. Okay, but in my proof, I have already made the assumption that the absolute value of x minus 3 is less than delta. So this has to be less than 13 times delta. Okay, so I just got my less than. Now I have to work it until I get my epsilon. How am I going to get an epsilon in here? What's delta equal to? So this is equal to 13 times the epsilon over 13, which just gives you epsilon. So I got the remaining part of my definition. We had to have a less than and an epsilon. There's my less than. There's my epsilon. So we are done. That tells us the limit as x approaches 3, 13x minus 29 equals epsilon. Sorry, not equals epsilon, equals k. Alright, we're not ready to work individually on this yet. We have to have more practice. Can you guys really fast try to clean your tables? Landon, can you spray? Matthew, would you hand out paper towels real quick?